Wet processing procedures usually create stress on a fabric. Continuous processes during preparation and dyeing, as well as preparation for drying, usually stretch the length and reduce the width. If these forces are great, they may exceed the elastic limit, thus permanently changing the fabric's relaxed dimensions. Finishing procedures may reduce or improve the dimensional stability of the fabric. If relaxation dryers, compactors, and/or cross-linking agents are used, then the residual shrinkage after wet processing can be reduced. However, if these measures are not used, then the improvement in shrinkage will be minimal or none at all. Apparel manufacturing processes can either reduce or increase the level of shrinkage of a fabric. The laying down of layers of fabric for cutting and the physical manipulation of the panels in sewing are examples of how shrinkage values can be increased. In fact, garments comprised of different fabric constructions may have some panels relax with handling, while other panels may grow. Garment care labeling and laundering practices have a direct influence on shrinkage performance. If the label calls for line or flat drying, then mostly elastic shrinkage will affect performance. However, if tumble drying is suggested, then all available residual shrinkage will be realized. If you follow a fabric through a processing route, it's easy to understand the impact different processing steps can have on shrinkage. First, look at the differences between the gray and finished relaxed dimensions. Gray delivered dimensions are those yielded off the machine. Therefore, after knitting, residual or laundering shrinkage will be equal to construction shrinkage. Finished delivered dimensions are those measured after finishing but before cut and sew. These dimensions should match the product specifications. By studying the difference between gray and finished delivered dimensions, it can be seen how processing has changed the dimensions. The goal in finishing is to reduce the shrinkage to the lowest possible level. After fully relaxing the finished delivered goods by repeated cycles of washing and tumble drying, the fabrics are said to be at their reference state. Evaluation of this relaxed data will reveal the most stable configuration the goods will ever achieve. These are the dimensions the consumer sees when they wash and wear the garments. This data is very valuable because the finished reference state is obviously different from the gray state, and it shows that the processing route has permanently changed the performance of the fabric. The data may point out potential problems with the construction or the processing in relationship to where the fabric wants to relax and the product specifications. The impact of stresses can be demonstrated by studying how the dimensions of the fabric change after each processing step. To demonstrate the effect of processing, a 24-cut interlock was marked with process shrinkage squares and was processed through a typical dye house sequence. At each step, the samples were tested for processing dimensional change and residual shrinkage. Some processes require that the fabric be pulled continuously through a range or cycled through a vessel in order to get a desired effect. Jet dyeing machines, becks, bleaching ranges, and pad and beam processing units all exhibit some stress on the fabric in the length direction during processing, but they do so at different levels. Equipment manufactured today applies less stress on the fabric than those of only 10 years ago. However, it's common for most of these machines to stretch fabrics in the length well over the gray state. Some soft flow and overflow jet dyeing machines actually do not stretch the fabric. They may relax the goods in the length. At the same time, unless restrained, the width of a knit fabric will completely relax upon wetting out in all these vessels because of the tensions on the fabric in the length. In this respect, a knit fabric acts like an accordion. This table shows how a cotton interlock fabric changed dimensions because of the forces applied during processing. Shrinkage and width data are shown after each processing step. These numbers clearly show the mobility of the fabric and how the tensions in each processing step change the residual shrinkage and the width. In the gray state, the fabric's tubular width was 33 inches and had no processing shrinkage. The residual or laundering shrinkage was 19% in the length and 15% in the width. After overflow jet processing, the interlock fabric had actually shrunk in the dye machine by 4.0% in the length. As is typical of cotton knits, the width had shrunk rapidly down to 29 inches. The residual washing shrinkage numbers indicate that the dyeing process had actually removed shrinkage from the fabric. However, the linear forces in water extraction lost all that was gained in the jet and caused an 8.0% growth in the length of the fabric over the gray dimension. This linear force was high enough to force the width of the fabric to be 27 inches. The residual shrinkage in the length from laundering was greater than that of the gray. The width grew by 3.5% because it was narrower than the fully relaxed state of the fabric. The fabric was then spread to 34 inches with overfeed and dried on a relaxation conveyor dryer with maximum mechanical action to a desired width specification of 30 inches. The dimensions lost in extraction were regained, as well as an additional 8.0%. The data shows that the relaxed dried goods were now 12% shorter than the gray goods. The residual length shrinkage was now 9.0%. By spreading and overfeeding, the desired finished width of 30 inches was met, and the width residual shrinkage was at 7.0%. These low residual shrinkage numbers ensured that compaction would be successful. Compaction was applied and accounted for a change of another 4.0% of relaxation. The residual shrinkage numbers were 5.0 by 8.0%. The width of 30.5 inches was delivered slightly above the cut and sew width to allow for loss in spreading of the goods on the cutting table. This data points out that the stress in the extraction step was severe and adversely affected shrinkage performance. Relaxation dryers are the most useful technique in reducing shrinkage in the dye house. Various systems are used, including conveyor belt systems, suction drum units, combinations of both, and continuous tumblers. All systems make use of mechanical action during drying to provide the energy to yield lower shrinkage. In order for a knit fabric to shrink during drying, certain actions must take place. The methods used to shrink the fabric must be able to overcome the static friction that exists within the knitted structure. Key factors for relaxation drying should include 1. Releasing of all tensions from the fabric. 2. The use of softeners to aid fabric structure mobility by reducing the static friction at yarn intersections. 3. Sufficient and uniform mechanical action to overpower all static friction within the structure, but at levels low enough to prevent stretching. 4. Mechanical action by airflow and belt vibration. 5. A flow uniform in intensity, varied in direction, but not offsetting in application. 6. Spreading of the fabrics with overfeed at the entry of the dryer or at a station just prior to the dryer. 7. Maintaining sufficient overfeed in all drying zones to allow for complete mobility in the fabric length during deswelling. 8. Tension-free precision plating of the fabric for apparel manufacturing or for the next processing step. Compaction is a mechanical process that uses physical force to compress the fabric in the length, thus reducing the length shrinkage. There are two basic systems used to compact fabric. The first type is the heated roll and shoe method. There are several versions of this type, however they all work on the same principle. Steam is applied as the fabric is put into contact with and under the control of a heated feed roll. Just enough moisture is applied to lubricate the yarns to allow the fabric to move freely. The fabric then moves between two heated shoes, which have special surfaces that grab the fabric in a controlled manner. The gap between these shoes is set to achieve compaction. When the fabric hits the surface of the heated shoe, the fabric slows, shortens, and compacts, based on the surface friction in the compaction zone. The fabric is then removed from the machine by a delivery roll that turns at a slower speed than the feed roll. The improper use of softeners can prevent the compaction force from being effective, due to slippage between fabric surfaces and machine components in the shrinking zone. Softeners may also reduce friction to the extent that the loops easily compact, but then lose the compaction during subsequent processing. Corrugation, or wrinkling of the surface because of improper loop movement during compaction, can be a big problem to finishers. This is a defect usually associated with overcompaction, but it can also be caused by improper or non-uniform softener application, as well as improper moisture content at the compactor. Although not normally a permanent defect, Corrugation can be removed by rewetting, drying, and compacting again at added costs. A second kind of compaction, belt compaction, utilizes either a rubber or felt belt that is stretched by flexing over a pressure roll. The fabric is laid on the belt while the belt is still stretched. Steam is applied as fabric enters the path, where it's pressed between the belt and a larger cylinder called a palmer unit, which is heated. Compressive shrinkage of the fabric with the rubber belt is obtained by the recoil of the belt when it is flexed around the palmer unit. After compaction on either system, the fabric is flat folded in a tensionless manner onto a table or truck.